Start.
Good afternoon, everybody. Today we are going to discuss about the gas turbine in the turbo machine. We know that in the turbo machine there is a energy transformation or energy transfer from fluid to rotor or rotor to fluid. Fluid to rotor with energy transfer in the turbine and rotor to fluid with energy transfer in the compressor. When we transfer the energy from rotor to fluid, then we have to supply some amount of energy like electrical energy. So in the compressor we have to supply some energy. The application of the compressor, if we think about the small scale, then the fan. Fan also works as a compressor. It transfers energy from rotor to fluid and blow the wind. But there is a limitation. With the wind, with the fan, we can increase the pressure that will be less than 0.7 bar. Similar working principle is for the blower. In the blower, change in pressure range is 0.7 bar to 3 bar. And if the change in pressure is more than 3 bar, then we call it as a compression.
No, it is, excuse me, ma'am, it is 0.07 bar?
Yes, 0.07 bar. But atmospheric pressure itself is 1.03 bar. So with the help of fan, the pressure of the air is increased from, it should be less than 0.7 bar.
0.7 or 0.07?
0.07 bar. It should be less than 0.07 bar. That's why we will not feel that the amount of pressure has increased or not. But if we test it with some equipment, then the amount of pressure in the room without running fan or with running fan will change. Then the energy transfer from fluid to rotor. This portion, the energy transfer from rotor to fluid, we discussed in the previous class. We have learned about the compressor, different kind of compressors like axial compressor, centrifugal compressor, reciprocating pump compressor, or about the pump. Today we are going to discuss about the turbine. In the turbine, we produce some amount of energy. Like application of the turbine, a hydraulic turbine, we transfer the water energy into mechanical energy. If we talk about the wind turbine, then we change the wind energy into the mechanical energy. If we discuss about the steam turbine, then we change the steam energy into the mechanical energy. And here today we will discuss about the gas turbine. So how to change the gas energy into the mechanical energy. The application of the gas turbine is like aircraft. We can use also in the industry and in the aircraft. Like aircraft, propulsion cycle, and the shaft power cycle. In the aircraft propulsion cycle, we have 5 kinds of application like ramjet engine, turboprop engine, turbojet engine, turbofan engine. And the shaft power cycle, we have marine-based installation or land-based installation to produce the power. The gas turbine itself divided into 2 part arrangement. One is open cycle arrangement, we can use atmospheric air plus a good quality of fuel. So the working fluid is air fuel mixture. The fuel should be a good quality because we conducted combustion chamber with turbine directly. If the quality of fuel is not good, then it will damage the turbine blades.
So how can we ensure the quality of fuel?
Quality of fuel, that is depends on the fuel should be erosionless, should not create any erosion, corrosion. It should not have high viscosity. If it is very high viscosity, fluid viscosity is high, then itself density will be more, and then it will damage the fuel. In the closed cycle, as a fuel, we will not use atmospheric air. We will use helium or helium carbon dioxide. And in the closed cycle, we circulate the same amount of fuel in the cycle continuously. We continuously not exhaust into the atmosphere, so it is more environment friendly. The cost of open cycle arrangement is less because it easily we can take atmospheric air and we can exhaust into the atmosphere. But here we have to make some more arrangement. Like we have to heat the air, we have to supply the combustion through the heat exchanger. So there one more equipment is heat exchanger. Then we have to cool down the exhaust gases temperature at the level of atmospheric. So there is also a condenser we have to add. So the complexity of the system is more complex. Closed cycle, this open cycle is more simple. Closed cycle is more environment friendly. Open cycle is less environment friendly. Cost of the cycle, the closed cycle cost is high. Open cycle cost is less. Today we first discuss about the closed cycle arrangement. In the closed cycle arrangement, there are one is a ideal cycle and another is practical cycle. Gas turbine. In the ideal cycle, we have some assumptions hypothetically. That is not realistic, that is called ideal cycle, gas turbine. First assumption is change in kinetic energy is negligible at inlet and outlet. Change in kinetic energy is negligible, means the velocity will not change in the compression and it also not change in the turbine. The second assumption, pressure drop is null or negligible. With the help of compression, we increase the pressure of the air. In the open cycle, we directly take the atmospheric air and we increase the pressure by adding some energy. So the pressure drop combustion chamber. This is a turbine. This is the power output. In the compressor, we supply atmospheric air at the stage 1. Then it is compressed, pressure has increased with the help of compressor. And we have supplied some fuel in the combustion chamber. This is the combustion chamber. And then the high temperature, high pressure exhaust gases are supplied to turbine. In the turbine, gases are expelled, and this is the product of exhaust gases. So, pressure drop is negligible in the combustion chamber. At different connecting devices, then head assumption is working fluid should be perfect gas. Working fluid should be perfect gas. What are the quality of perfect gas? When we call it, it is a perfect gas. Sir, tell me about it.
I think it must have some, does not have correlation with each molecule.
Sir, means that follow the ideal gas laws.
Yeah. That follows the ideal gas laws.
PV बराबर P is equal to nRT.
PV is equal to
Like gamma should be equal to 1.4. The ratio of specific heat. Gamma is the ratio of specific heat. Cp upon
CV.
specific heat at constant pressure and specific heat at constant volume. That ratio of specific heat should be equal to 1.4. Follow the ideal gases laws. And the fourth law is mass flow rate should be constant. Mass flow rate should be constant. Whatever amount of air we are taking from the atmosphere, that should be constant. Whatever amount of fuel we are supplying into the combustion chamber, that should be constant. And the fifth assumption is expansion and compression. The expansion and compression. Then, if we have two diagrams for the open cycle, one is the PV diagram and another is TS diagram. In the PV diagram, first compression. We compress the air from 1 to ideal. Then we supply the heat in the combustion chamber 2 to 3 at constant pressure. Then the expansion will occur also again as a adiabatic process and heat rejected at constant pressure. Similarly, in the TS diagram, change in entropy is constant. Heat supplied, expansion, and the exhaust gases. So, the compression, the cycle 1 to 2, we compress the gases into the compression. That compression. And in the turbine, we expand the gases through the cycle 3 to 4. That is called expansion. any loss 1, 2, 3, 4 continuously should be reversible, and compression and expansion occurs at a constant entropy. Change in entropy is negligible. Change in entropy is negligible comes in the thermodynamics law, like third law of thermodynamics. That is totally based on the change in entropy. If we change the absolute temperature equal to 0, like I write it, if the temperature, absolute temperature, reach to 0, then change in entropy will become 0. But absolute temperature will not become 0 in the finite number of iterations. If we consider an infinite time duration, then it will be achieved. And we are talking about the cycle within a second or microsecond. So these 5 are the main assumptions.
Now, is it possible that we can summarize all these assumptions once again? Means whatever we discussed, what are the attributes of an ideal gas turbine? So, is it possible to summarize it?
Yes. First, change in kinetic energy should be negligible at inlet and outlet. Means change in velocity at compressor and in turbine should be 0. The second, mass flow rate throughout the cycle is constant. Means whatever amount of air and fuel we have supplied, that should be maintained constant. The third assumption is the compression and expansion process should be adiabatic and reversible. Change in entropy is negligible. And fourth, pressure drop at different connected devices like combustion chamber, turbine at the output shaft should be negligible. And working fluid should be a perfect gas. If we are talking about a practical cycle, because I have discussed about the ideal and practical, we take further the ideal cycle first, but in the practical cycle, the change in kinetic energy is not negligible. The pressure drop is not negligible at different connecting devices like combustion chamber, turbine, output shaft, and then the mass flow rate. Mass flow rate, whatever amount of air plus fuel we supply, that will not be constant throughout the cycle. The working fluid will not be perfect gas. Means the gamma ratio of the specific heat is always less than 1.4. And the fourth, the compression and expansion process are change in entropy will not constant. This is the TS diagram. 1, 2, 3, 4 is a TS diagram for ideal cycle. 1, 2, 3, 4 is for the ideal cycle. And 1, 2 days, 3 to 4 days is for the practical cycle. Then amount of energy than the work done on the system. The work done by compressor WC. How to calculate the work done? First, I like to discuss about the governing equation that we have studied several times. So, tell me about the governing equation of thermodynamics. How thermodynamics works? How to deal different kind of systems? In the system, what do? We supply some amount of heat.
U plus P.
With the help of heat, we do some work that is called shaft work. Because here we get some amount of work at the shaft. And then, what will happen during the whole process? There might be change in enthalpy. There might be change in kinetic energy. Or there might be change in potential energy. This is the governing equation generalized. In the any field, whatever amount of heat supplied to the system will convert it into the work done plus change in enthalpy plus change in kinetic energy plus change in potential energy. In the open cycle arrangement, we have taken assumption change in kinetic energy is 0. The change in potential energy will depend on the altitude and GH. Here, change in height is negligible, so change in potential energy is also 0. In the compressor, we will not supply directly any kind of heat. In our compressor, then we have not supply any kind of heat. It's supplied through the combustion chamber. So the heat supplied to the system is also negligible. So the work done should be equal to change in enthalpy. It will be negative, it will be positive, it depends on how the process will go. So the compression work. First is the compression or your compression work. During the compression cycle, whatever amount we done, that we call compression work. That is change in the enthalpy. Change in the enthalpy is equal to S2 minus H1. Or we can say Cp into T2 minus T1. Similarly, the turbine work W. Turbine will work during the cycle 3 to 4. Compressor will work during the cycle 1 to 2. Here, we take the atmospheric air, compress at the high pressure and supply to combustion chamber. The compressor works in cycle 1 to 2. So change in temperature during the cycle 1 to 2. Similarly, turbine work will change the temperature during the cycle 3 to 4. But we know that whatever amount of temperature supplied to the turbine, then the gases are expanded and we produce some amount of power from the shaft and exhaust the gases to N1 because it is open cycle. Then the work done is S3 minus S4 and it will be Cp3 minus T4. Then the work done, heat supplied with the help of combustion chamber. So whatever amount of heat supplied here, heat supplied to is equal to, yes, Anamika can tell me about the heat supply. Which process you will add the heat to the system? With the help of the systematic diagram provided with the help of PVOTS diagram.
1 to 4.
1 to 4? No. Combustion chamber is is located between the 2 to 3. We added fuel during the cycle 2 to 3. So heat supply should be 2 to 3. So that is S3 minus S2 is equal to Cp T3 minus T2. Then we like to calculate net work because whatever amount of work done by the compressor that we supply to the system and whatever amount of done by the turbine that we get as a amount of mechanical energy. So what is the net work done? The net work done should be our main aim to establish this cycle is to get some amount of mechanical work, to produce some power. So the net work done, Wn is work done by turbine minus work done by compression. So that should be Cp T3 minus T4 and then turbine work done T2 minus T2. If we like to calculate, our main aim is that develop such kind of engine to maximize the net work done, to maximize the efficiency of the system or the engine. Then if we calculate the maximum work done, then we can calculate in this manner. T3 upon T1. I take out the T1 outside. T4 upon T1 minus T2 upon T1 plus 1. This minus becomes plus. If I multiply this T3 and T3, it will not affect. Let take T3 is the maximum temperature that we achieve during the cycle. This is the maximum temperature and T1 will be the minimum temperature. Then we can take T3 upon T1 is equal to T. Similarly, process 1 to 2 and 3 to 4 is an adiabatic process. We know that the heat supplied at constant pressure, heat rejected at constant pressure, expansion and compression will occur as a adiabatic. Adiabatic cycle means PV to the power gamma is equal to constant. Then we can say that P1 V1 to the power gamma is equal to constant. P2 V2 to the power gamma means P1 V1 का gamma constant means क्या होता है? Whatever condition at the point 1 that should be at the point 2. We know that working fluid should be perfect gas. So PV is equal to RT. With the help of this relation, we can calculate the relation between P2 compression. With the help of this relation, PV is equal to P is equal to RT upon P. So that this relation becomes P1 1 minus gamma T1 gamma is equal to P2 1 minus gamma T2 gamma. If I write T2 upon T1 is equal to P1 upon P2 to the power 1 minus gamma upon gamma, then I will also write it P2 upon P1 to the power gamma minus 1 upon gamma. This, so whatever ratio we achieve in the compression 1 to 2, that is called compression ratio. That is called R. So here R is power gamma minus 1 upon gamma. So what is that? T2 upon T1. That we can assume it will be a constant. Then we can solve it further for optimum work. Then this becomes Cp T minus T upon C minus C plus 1. because the 2 to 3 and 1 to 4 is constant pressure cycle. To maximize the work, what we will do? We differentiate first and put equal to 0. So here we will differentiate with respect to C and put equal to 0. Then it will become T upon C square minus 1 is equal to 0. So C becomes root of T, right? This is the maximum work we can achieve through the cycle. Then the efficiency of the cycle. Is there any doubt?
No, ma'am. This is complete.
The maximum efficiency or efficiency of the cycle. Of the system. The maximum efficiency, whatever amount of work done divided by heat supply. So net work done is Wn and divided by heat supply. Amount of work done, that is Cp T1 T minus T by C minus C plus 1, and the heat supply Cp T1, if I solve the equation T2 upon T1 upon T2 upon T1, then it will become T minus C. So efficiency of the simple system is, I can write in this manner. Then I can say the efficiency is 1 minus 1 upon C, or the efficiency of a simple cycle is R to power gamma minus 1 upon gamma. This is the efficiency of simple gas turbine cycle. We can improve the efficiency of simple gas turbine cycle by adding some accessories. For example, we can increase the net work done by reducing the amount of work done by compression. Whatever work done by the compression, we can reduce by using accessories, that is called intercooling. This is one way to improve the efficiency of system or to improve the net work done. Another, by increasing the turbine work done. Whatever work done by turbine, we can increase with the help of reheating. And second thing, we can reduce the amount of heat supplied to the system by adding. We can reduce the amount of heat supplied to the system by adding a heat exchanger. Or we can also say it regeneration of exhaust gases. So these are the three ways to improve the efficiency or net work done of open cycle. By adding a intercooling, we can reduce the amount of work done by compression. By adding a heat exchanger, we can reduce the amount of fuel is supplied to the system, and by increasing the turbine work done by adding a heat repeater. Before going to discuss about the improvement of net work done or efficiency of system, first I would like to discuss one numerical for a simple gas turbine cycle. Please write a numerical for simple gas turbine cycle. Write a numerical. Compute the indicated mean effective pressure. Compute the indicated mean effective pressure. Indicated mean effective pressure and efficiency of a Joule cycle and efficiency of a Joule cycle is the temperature at the end of combustion. Is the temperature at the end of combustion is 200 Kelvin. At the end of combustion is 200 Kelvin. And temperature and pressure before compression and temperature and pressure before compression is 350 Kelvin and 1 bar. Pressure ratio is P2 upon P1 is 1.3. Assume Cp is equal to 1.005 kilojoule per kg Kelvin. So first we calculate the mean effective pressure and the efficiency of a simple gas turbine cycle. Here we have temperature at the initial stage and pressure is 1 bar. Pressure ratio is given R is equal to 1.2. So the pressure at the point 2 after exiting from the compressor should be 1.3 bar. That is given to us. The ratio is given to us. Maximum temperature is given. The maximum temperature when will be occur when the exhaust gases come out from the combustion chamber at the point 3 as per our cycle. Then the temperature of the exhaust gases is maximum. Then expand and temperature will reduce isentronically as per our assumption. Then with the help of adiabatic relation, we know that T2 upon T1 is equal to P2 upon P1 to power gamma minus 1 upon gamma. Specific heat given to us 1.5, so the gamma should be 1.4. Then the 1.3 to power 1.4 minus 1 divided by 1.4. So the T2 should be 350 into 1.3 to power 0.4 upon 1.4, and that will become equal to 327.2712. Please carry your calculus with you and calculate faster than me. Then, in the similar, during the expansion process, 3 to 4, T3 upon T4 will also equal to T1 की power gamma minus 1 upon. Because we know that during the ideal cycle pressure drop in the combustion chamber and turbine is negligible. So that T4 will be equal to T3 and that is given to us 2000 divided by 1.3 की power 0.4 divided by 1.4 and that will become equal to 1855 Kelvin. Now we know the temperature T1, T2, T3, T4. So we can calculate the work done by the compressor turbine and whatever amount of heat is supplied to the system. So whatever amount of heat supplied to the system, for the first work done by the compressor, that should be Cp into T2 minus T1, that is 327 minus 350, that will become equal to 27 kilojoule per kg. Then the work done by the turbine, that will be, we know that turbine work done is Cp T3 minus T4. So that will become equal to 0.05 into 2000 minus 185 and that will become equal to 118 kilojoule per kg. Similarly, the work done, heat supplied to the system. Heat supplied to the system, we supply the system heat to the system during the combustion and Q is equal to Cp T3 minus T2 and that will become 1.005 2000 minus 377 and that will become equal to 200. The amount of heat supplied to the system will become 100. 1630 kilojoule per kg. We know the efficiency of the system is net work done upon heat supply. And net work done will be turbine work done minus compression work done upon heat supply. Turbine work done at here is 180 minus compression work done is 27 divided by heat supplied is 1630. If you calculate the efficiency, then you always divide by the 100 because we calculate the percentage and that will become equal to 7.39%. So this is the efficiency of this side. If we supply the temperature, so if we supply the atmospheric air with the compression ratio 1.3, then the efficiency of the system will be so reduced. We know that from the formula, the efficiency of system is depends on the compression ratio. We know the formula, eta is equal to 1.1 upon R to power gamma minus 1. If the compression ratio is small, then this parameter will be big and then the efficiency will be reduced. So our main aim is to achieve the maximum pressure ratio or compression ratio. But again, by increasing the pressure, the temperature will also increase. We have seen with the help of this diagram. If the amount of pressure is increased by 1.3, 1 to 1.3, then the temperature is increased temperature will also reach more than 700. And if the temperature will reduce much, then the fuel will burn here only, air itself will burn. So we have to take care of things. That's why we want to get the maximum pressure with the help of compressor by adding some accessory like intercooling. One. Second, in this numerical, they ask mean effective pressure. The mean effective pressure. With the help of PV diagram, we have seen the mean effective pressure is what? Mean effective pressure is made work done upon change in volume. Change in volume, if you see our PV diagram, then the maximum change in volume is V4 minus V2. Maximum volume when gases we are exhaust to atmosphere V4, and minimum volume when we compress the gases at high pressure. So the change in volume will be V4 minus V2. We need to calculate here volume. We know the pressure and temperature at each stage. We know that our working fluid is perfect gas. So we know the relation PV is equal to RT. To calculate the volume at point 2, that will be P2, V2R, T2. Then V2 is RT2 upon P2. We know that R is a gas constant, and that is 287. We know the temperature 377 at the point 2, and we know the pressure is 1.3. Here, pressure is given through the bar. 1.3 bar. If we change in the, first we have to change unit. If we change in the Newton per meter square, then it becomes 1.3 into 10 to the power 5 Newton per meter square. We know the gas constant is always kilojoule per kg Kelvin. Then we have to multiply here 10 to the power minus 5. Then our volume V2 will be 0.833 meter to the power meter cube per kg. Similarly, we can also calculate volume at point 4 when the gases are exhausted from the turbine. V4 should be R T4 by P4. We know that heat is rejected at constant pressure. Means P4 should be 1 bar. So the R is 287. T3, T4 we have calculated, it is 1855, and T4 is 1 bar or 1 into 10 to the power 5 Newton per meter square. So the volume at point 4 is 5.35 meter cube per kg. So the mean effective pressure will be, the amount of net work done is 118 kilojoule per kg divided by change in volume 5.325 minus 0.8 3, 3, 5. First again take the unit. We know that this unit is kg, sorry, meter cube per kg for the volume. So we have to change first kilojoule into joule. We know the unit of joule is Newton into meter upon kg. And we know that unit of change in volume, it is approximately 4.28, and its unit is meter cube per kg. So kg to kg cancel, 1 meter to cube cancel, and it becomes Newton per meter square, and that will be equal to, here change in pressure will be equal to 26250 Newton per meter square, or you can say 0.2625 bar. So mean effective pressure is 0.2625 bar. This is the mean effective pressure, and we have said that in the compressor we change the pressure by 0.3, 1 to 1.3. Change in the pressure occurred during this process 0.3, and we get the mean effective pressure. Whatever amount of pressure will create the work, that amount of work we get, because mean effective pressure depends on the net work. So, what the mean effective pressure will be maximum, then we can say our system will be more efficient. How much time?
55 minutes.
To improve the system, we can increase the net work done. We can also say we can increase the indicated mean effective pressure, or we can also say we have to increase the efficiency of the cycle. First, I like to introduce one thing, how to improve the efficiency. Efficiency we can improve by the net work done. So efficiency is turbine work done minus compressor work done upon heat supply. So efficiency one can improve by increasing turbine work done, by decreasing or by reducing compressor work done, or by reducing or decreasing the amount of heat supplied or added to the system. We can decrease the amount of heat supplied to the system with the help of adding a heat exchanger. Like we have a simple gas turbine cycle. This is a compressor, and this is a turbine, and this is a combustion chamber. This is the compressor and turbine. This is a shaft to produce power output. These are the exhaust gases. We are through the simple cycle, we are directly supplied to and that is too much high temperature. If we utilize this temperature to heat the gases from the exit of compression, the exit of compressor from our previous numerical temperature is 377